Swayam Prabha. Digital India. Educated India.
So another basic element which we can consider now is what is known as a mutual inductor. Okay, this is related to the inductor. We know that if you have a voltage V across an inductor L and a current I through the inductor L, the flux linkage is given by L times I, and the voltage is given by the time derivative of the flux linkage, which is L times the time derivative of the current. Okay. Now, because the magnetic field of an inductor extends outside the inductor, it turns out that you can place another inductor, and to distinguish between these two, I will call this L1, I1 and V1, and I will call this L2, I2 and V2. Okay. They can be arranged to be close enough to each other such that when you pass a current I1 through L1, it induces a magnetic field in L2 and causes some flux linkage there as well. Okay. So the flux linkage in inductor L1 is related to I1 as well as I2, and similarly the flux linkage in L2 is related to both I1 and I2. Okay. So this is possible because the magnetic field in an inductor can spread outside the physical extent of the inductor. Okay. So in such a case, what happens is that the flux linkage in the first inductor is some L1 times I1, which is what we expect knowing what we know about inductors, but it also related to some other constant M times the current in the second inductor. Okay. And similarly, the flux linkage in 2 is related to L2 I2, which is what you expect given the second inductor, plus the same mutual inductance times the current in the first inductor. Okay. So the same coefficient appears here and here. We won't discuss why that's the case, but that's a fundamental property. That is, the proportionality constant between I2 and psi 1 is the same as between I1 and psi 2. Okay. And this constant is known as the mutual inductance between L1 and L2. Okay. So because of this, again we can get the current voltage relationships, which are that V1 is L1 di1 by dt plus M di2 by dt, and V2 is M di1 by dt plus L2 di2 by dt. Okay. So this is a mutual inductor, and the voltage depends on the rate of change of both coils. Okay. This L1 is called the self inductance of coil number 1, and L2 is called the self inductance of coil number 2, and this M is called the mutual inductance between these coils. The self inductance of coil 1 is the inductance it would have, which gives the relationship between voltage and current if the coil 2 was not even present. Okay. Similarly, for the self inductance of the second coil, this mutual inductance appears only when you bring these two coils together, so that the magnetic field from one inductor influences the other inductor. Okay. And these are the current voltage relationships. Clearly, this is not a two terminal element. There are 4 terminals, 2 for each inductor. Okay. Now, if you have been careful, you would have noticed some ambiguity. That is, let me take the 2 coils again. If I take the first coil by itself, I will define V1 and I1 according to the passive sign convention, and to remove any ambiguity, let me call these terminals A and B. And I could equally well have defined this A and B mark the physical terminals. I could equally well have defined V1 in the opposite direction, and to be consistent with passive sign convention, I have to consider I1 in this direction. Okay. Now, when I have coil number 2, again I have the same 2 possibilities. Okay. I have C and D, and I can take V2 this way and I2 this way, or V2 in this direction and I2 in that direction. Okay. That is, I can consider C to be the positive terminal for defining the voltage, or D to be positive terminal for defining the voltage. This makes no difference to the self-inductance definition, because direction of I2 is also reversed. Okay. Because if I wrote V2 is L2 di2 dt, I could also write minus V2 as L2 time derivative of minus I2, which corresponds to the directions chosen in the bottom picture. Okay, if I define this voltage to be something else, it's simply the negative of that voltage, and this current is the negative of that current. Okay. But when you have a mutual inductor, there is a problem. Now, I could define coil 1 to be like this and coil 2 to be like this, or like that. That makes a difference for the mutual inductance, because this current is opposite of that current. If I took the flux linkage to be L1 times I1 plus M times I2, okay. So, there is no ambiguity for the self-inductance part for this itself, but for the second part, if I take coil 2 I2 in this direction, I get something, and if I take it in the opposite direction, I get the negative quantity. Okay. So, to remove this ambiguity, when you have a mutual inductor, let us say you have V1 and I1, you place dots next to the two coils, okay, and you have V2 and I2. These dots are there so that the sign ambiguity in the mutual coupling is removed. So, once you are given the dots, what you do is, let us say you choose V1 and I1 like this. Let me remove this one. Let us say you choose V1 this way. For the definition of V1, the terminal with the dot is positive and I1 flows into the dot. Then you take V2 also with the terminal with the dot being positive and I2 flowing into the dot. Okay. With this, V1 will be given by L1 di1 by dt plus M di2 by dt, and V2 will be M, the time derivative of I1 plus L2 time derivative of I2. Okay. So, this removes the sign ambiguity. That is, you take both currents going into the dots and the voltages according to the passive sign convention, then you get a plus sign here. Okay. If for whatever reason you choose to consider I1 flowing into the dot I2 flowing into the terminal without the dot. Okay. Then of course you have to choose voltages consistent with passive sign convention. That means that the positive terminal of V1 is wherever I1 is flowing into, and the positive terminal of V2 is wherever I2 is flowing into. In this particular case, V1 will be L1 di1 by dt minus M di2 by dt, and similarly V2 will be minus M, the time derivative of I1, plus L2 time derivative of I2. Okay. So as you can see, the sign of the induced voltage from the other coil, that is the mutually induced voltage, is what changes. Okay. The self-inductance parts, which are given by this and that, do not change. Okay. So when you specify a mutual inductance, you also have to specify the dots so that there is no ambiguity in the sign of currents and voltages. Okay.